What you are seeing is the blueprint for the Hydro-Gravitational Device. It is the simplest perpetual motion machine you can build yourself at home. It has four main components: two containers full of water, one normal tube, and an asymmetrical tube. The normal tube does exactly what you think it does. It simply pours water from the higher container into the lower container. No need for an explanation there. The asymmetrical tube is the one that does all the magic here. It takes water from the lower container and pours it into the higher container. And it does this continuously and without requiring any energy, motor, or a water pump of any kind. So, when the device is working, what you see is that the asymmetrical tube will continuously lift the water from the lower container and into the higher container, and then the normal tube will send the water back down again, creating an infinite loop. To understand how the asymmetrical tube does what it is supposed to do, let's go back to the origin of the idea itself. There is an old Hollywood cliché, used in dozens of movies and TV shows, where a thief is trying to steal gasoline from a car. What is important here is the method used by the thief to steal the gasoline. This is how the scene usually goes. The thief opens the gas tank of the car, then he inserts a long tube into the gas tank, then sucks on the tube for a few moments until the gasoline starts coming out of it, then places the end of the tube inside the container he brought to carry the stolen gasoline. After he does this, the gasoline will begin to pour out of the tube and into the thief's container on its own. The thief won't have to do anything else. This process will continue on its own as long as the gas tank has any gasoline left. It doesn't matter how big the gas tank is. It might be as large as the Atlantic Ocean. This method will empty it completely. It is important to point out that this method does work. It is not some Hollywood invention concocted by the same kind of brain-dead screenwriter who thinks that cold fusion causes things to freeze. This method has been known for centuries. It was probably discovered not long after the invention of tubes themselves. And it is a very useful method for emptying large containers where the only opening is at the top, and for some reason you cannot just lift the container and turn it on its side. Now let's take a closer look at what is happening here. The gasoline inside the gas tank is pulled inside the tube, then this gasoline moves upwards inside the tube until it reaches the opening of the tank, then it moves downwards toward the container. The most important detail here is that the gasoline will go up as it travels the short distance between the tank and the opening of the tank. If the gasoline moved downwards the entirety of the trip, there would be no need for an explanation beyond gravity pulling the gasoline down. But the gasoline does move upwards on its own accord, and this detail is the one that requires an explanation. First off, let's think about the tube as having two separate parts. The right part that goes from the opening of the gas tank and into the gas tank itself, and the left part, which goes from the opening to the thief's container. Both parts are full of gasoline, and in both cases, gravity is trying to make the gasoline move downwards. The first question that arises is this one: why doesn't the gasoline just split in two, with one portion going down to the gas tank and the other going down to the container? The answer is that the tube has no air inside of it. It only contains gasoline. If the gasoline tried to split apart, it would create a vacuum at the top of the tube, and the forces preventing that vacuum are stronger than the forces trying to move the gasoline. So as long as the thief ensures that no air enters the tube, the gasoline will be forced to act as a single entity, and the whole of the gasoline inside the tube must move in the same direction. This direction depends on the forces involved in the system. In this case we have two main forces, both of which are the result of gravity trying to pull the gasoline down. The gasoline in the left part of the tube is trying to go into the container, while the gasoline in the right part is trying to go back into the gas tank. This starts a tug of war between the two forces, and the winner will decide in which direction the whole of the gasoline will move. In this case, the left part of the tube going into the container is longer than the right part of the tube going into the gas tank, and thus it contains more gasoline. More gasoline means more weight, and thus a greater force created by gravity trying to pull it down. So the left part of the tube wins the tug of war, and the gasoline will move toward the container. Then comes the most important part. As the gasoline moves down the left part of the tube and pours into the container, it pulls the gasoline on the right part of the tube and forces it into the left part of the tube to replace any gasoline that fell out of the tube. Likewise, the right part of the tube will suck gasoline from the gas tank to replace any gasoline that moved to the left part of the tube. The result of this is that no matter how much gasoline passes through the tube, the amount of gasoline inside the tube remains the same, and thus the forces inside of it remain the same. And this process will continue on its own accord, as long as there is any gasoline left in the gas tank. As stated earlier, this method does work. It is trivial for you to test it yourselves at home if you want to see it in action. The problem is that this method is not very useful by itself, because ultimately it only works because the gas tank is higher than the thief's container. All you are doing is moving the gasoline down, which is not particularly impressive on its own. But what if you wanted to use this method to move water upwards from the lower container and into a higher container? Is it even possible? If you use the exact same tube used by the thief, then it won't work. The left part of the tube would invariably be much shorter than the right part of the tube, so the right part would contain more water and thus a greater force. This will cause the water to move down, not up as we want it to. The solution is as obvious and simple as it gets. The amount of water in each part of the tube is the result of the length of the tube and its diameter. If you cannot alter the length of the tube, just alter the diameter to ensure that the left part is much wider than the right part of the tube. This way, the left part will contain much more water than the right part, and the tube will work exactly as it did for the thief, moving the water from the right part toward the left part. In other words, it moves the water upwards. And like with the thief's example, the water in the asymmetrical tube should be moving upwards continuously on its own accord, so long as there is water left in the lower container. One very important detail that you must not forget is that the asymmetrical tube must be full of water before set in place. Just like the thief had to suck on his tube to ensure it was full of gasoline, you are going to need to use a water pump to fill the asymmetrical tube with water before you begin. Luckily, you only need to do this once, and after that, everything will work on its own without requiring any energy or fuel of any kind. You also need to ensure that no air enters the tube while it is working, because if too much air enters, then it would allow the water to split in two without creating a vacuum, and we need to avoid this. This is very easy to do. Just ensure that both ends of the asymmetrical tube are below the water level in their containers, and no air will be getting into the tube. In case this explanation is not enough to convince you that it works, let me explain it in a different way. The water in the wide part of the tube is essentially in free fall and trying to move down. Since there is no air inside the tube, when the water tries to move, it will create suction at the top of the tube with a force that is equal to the weight of the water inside the tube. Let's say that X represents this force. On the other hand, we are trying to make the water on the thin part of the tube move upwards. In order to do this, we need to apply a certain amount of force. Let's say that Y represents this force. Imagine that we are trying to lift this water by connecting a syringe to the top of the tube and pulling on the plunger. Y is the amount of force you would need to apply to the plunger to cause the water to move upwards. In other words, X represents the amount of force we have at our disposal, and Y represents the amount of force we need in order to make the water move upwards. And so long as X is greater than Y, the water will move exactly as we want it to. That is all there is to it. The exact values of X and Y depend on the amount of water in each part of the tube. In the case of Y, in order to lift the water, you need a force that is greater than the weight of the water inside the thin part of the tube. That is, to lift 1 kilogram of water, you will need a bit more than a kilogram of force applied to it. There are other forces that add up to Y too. There is friction caused by the water colliding with the tube as it moves upwards, and there's also some force necessary to suck the water from the container and into the tube. The most important point is that both X and Y are proportional to the amount of water inside each part of the tube, and you can directly control this amount of water simply by altering the diameter of the tube on each part. You can design the tube so the wide part contains 10 liters of water and the thin part contains only 1. If that is not enough, just make it 20 liters in one part and half a liter in the other. Since the values of X and Y come from known variables that you can control directly, you can literally decide beforehand what values you want for X and Y to have, and design the tube to produce those exact values. In other words, making the asymmetrical tube work as advertised is simply a matter of designing it with the right proportions, and nothing else. And so, if you designed it properly, the asymmetrical tube will move the water from the lower container and into the higher container, and will continue doing so on its own until the lower container runs out of water. This brings us back to the hydro-gravitational device. All you need to do now is to add a normal tube that dumps the water from the higher container back into the lower container, and this will create an endless loop. In other words, a perpetual motion machine. Of course, a perpetual motion machine is little more than a mildly interesting party trick on its own. It only becomes truly groundbreaking when you fit a hydroelectric generator into the normal tube, so it can continuously generate electricity in a way that requires no fuel whatsoever and produces no waste or emissions of any kind. But that's a story for a future video.